Tonight, we're going to confront a truth that your eyes will fight to reject every time you gaze up at the darkness above you. The sky looks alive. Stars shimmer across the velvet black. Galaxies wheel silently through unfathomable voids, and luminous nebulae drift like painted smoke through the fabric of space. It feels crowded, it feels full, it feels like a place where matter reigns. But when physicists turn their instruments outward and start measuring the cosmos on its grandest possible scale, they uncover something that has no business being true. Almost nothing is there. Matter is astonishingly scarce. The gulfs separating galaxies are stretching wider with every passing second, and the invisible force responsible for all that stretching is only tightening its grip, pushing faster, pulling everything apart, and showing no sign of slowing down. By the time this video ends, you will understand why the universe is expanding for a reason, what scientists have learned about the forces driving that expansion, why they cannot stop it even if they wanted to, and why this particular chapter of cosmic history is more fragile and more precious than almost anyone appreciates. Before we dive in, if exploring the deepest questions about space and time is the kind of thing that keeps your mind awake at night the way it does ours, take a moment to leave a like or hit that subscribe button. It's a small thing, but it's what allows us to keep building these journeys for curious minds like yours. Now, let's get into it. On any clear night, if you manage to escape the light pollution of a city and let your eyes adjust to the real darkness, a view unlike any other opens above you. Thousands of individual stars resolve against the black. The pale river of the Milky Way arcs overhead, flowing like luminous mist from one horizon to the other. It is one of the most moving sights the natural world can offer, and it gives you the overwhelming, visceral impression that the cosmos is stuffed to bursting with matter. All that light, all those pinpricks of fire. Surely the universe must be saturated with substance. But here is where reality begins to betray your senses. Every single star you can make out without an instrument belongs to our immediate cosmic backyard. The most distant pinpoints your unaided eye can detect sit perhaps 15,000 light-years away. That distance is staggering by any human measure, almost incomprehensible. And yet the Milky Way itself stretches roughly 100,000 light-years from end to end. Everything you see above you represents less than 15% of a single galaxy. And that galaxy is merely one among hundreds of billions scattered across the observable universe. So that sky packed with stars you find so impressive is really just your front porch. Imagining the universe looks anything like that scene is a little like standing barefoot in your garden and concluding that the entire planet must look exactly like your lawn. Now let's bring a telescope into the picture and watch what happens. Point a powerful instrument at what appears to be empty darkness, a region of sky with absolutely nothing visible to the naked eye, and wait. In 1995, astronomers did exactly this with the Hubble Space Telescope. They selected a tiny patch of sky in the constellation Ursa Major, a patch so minuscule that it would take roughly 12 million such fragments to tile the entire celestial sphere. And then they asked Hubble to simply stare into it for 10 days straight, accumulating long exposures, collecting every stray photon that drifted into the instrument. What came back was unforgettable. Approximately 3,000 galaxies crowded into a region of sky about the size of a grain of sand held at arm's length. Every smudge, every blur, every fleck of light in that image was not a star, but an entire galaxy containing hundreds of billions of stars of its own. This image became known as the Hubble Deep Field, and it revealed something that rewrote the way astronomers thought about the universe. Wherever you look, no matter how empty the patch of darkness seems, galaxies swarm through it by the billions. Astronomers repeated the experiment in different directions. The result was the same every single time. Galaxies everywhere, distant galaxies, nearby galaxies, spirals, ellipticals. Irregular galaxies colliding in slow-motion gravitational ballets. The evidence seemed unambiguous. The cosmos must be overflowing. But then, scientists did the math. And the math told a completely different story. Let's actually calculate how much matter fills the universe, because the numbers are where the emptiness reveals itself. The observable universe spans roughly 93 billion light-years across. That represents the farthest reach of anything we can detect in any direction. Light has been traveling since the Big Bang 13.8 billion years ago, but space itself has been growing during that entire journey, so the original sources of the oldest light are now considerably more distant than those 13.8 billion light-years would suggest. Inside this enormous observable sphere live approximately 2 trillion galaxies, 2,000 billion of them. Each galaxy contains somewhere between 10 million and 1 trillion stars depending on its size, with an average of perhaps 100 billion stars per galaxy. Do the arithmetic. 2 trillion galaxies multiplied by 100 billion stars each gives you roughly 200 billion trillion stars. Written out, that is a 2 followed by 23 zeros. 200,000 billion stars. It sounds absurd. It sounds like more than enough to fill anything. But now compute how much actual space those stars occupy. A typical star like our Sun has a diameter of about 864,000 miles. Plug that into the formula for the volume of a sphere, 4/3 pi times the radius cubed, and each star occupies roughly 1.4 billion cubic miles. Multiply that by the total number of stars in the observable universe, and the collective volume of every star that exists comes out to about 2.8 times 10 to the 32nd power cubic miles. 2.8 followed by 32 zeros. Surely that must occupy a meaningful fraction of space. Except the observable universe has a radius of about 46.5 billion light-years, which converts to roughly 4.4 times 10 to the 26th power miles. A sphere with that radius has a volume of approximately 3.6 times 10 to the 80th power cubic miles. Now divide one figure by the other. Stars, all of them combined, occupy about 7.8 times 10 to the negative 49th power of all the available space. That is a decimal point followed by 48 zeros and then a 7. Stars take up less than 1 quadrillionth of 1 quadrillionth of 1 quadrillionth of 1% of the universe. Let me translate that into something tangible. If you took the entire observable universe and shrank it down to the size of planet Earth, every star inside it, all 200 billion trillion, would collectively occupy a region smaller than a single atom. Actually much smaller than that, more like a single proton. And we are not even finished, because most of the interior volume of a star is itself nearly empty. The nucleus of an atom, where essentially all the mass resides, occupies only about 1 trillionth of the atom's total volume. Everything else is empty space through which electrons move. Even the solid matter inside stars is overwhelmingly emptiness pretending to be substance. We have not even mentioned the space between the stars inside a galaxy, or the enormous distances separating galaxies themselves. The Milky Way contains about 200 billion stars, spread across roughly 100,000 light-years, which converts to around 588 trillion miles. Our closest stellar neighbor, Proxima Centauri, sits 4.2 light-years away, or roughly 25 trillion miles from the Sun. The separation between stars is thousands of times larger than the stars themselves. If you scaled the Sun down to a single grain of sand, just 1 millimeter across, the nearest star would be about 19 miles away. Picture that. 2 grains of sand separated by 19 miles of silent nothingness. That is the ordinary spacing inside our own galaxy. Galaxies themselves are separated by gulfs that dwarf even this scale. The Andromeda Galaxy, our nearest large neighbor, sits about 2.5 million light-years away. The Milky Way spans 100,000 light-years, so the distance to Andromeda is 25 times the width of our own galaxy. In our grain of sand analogy, that is like 2 sand grains placed on opposite ends of a football field. And between our galaxy and Andromeda, there are only a small handful of tiny dwarf galaxies. The rest is nothing. Vacuum. Dark, cold, empty space. And this, remember, is the local group, one of the denser pockets of the universe. In many other regions, galaxies lie vastly farther apart. Galaxy clusters are themselves separated by colossal voids containing almost nothing at all. So the universe is mostly vacant space between stars, wrapped in even emptier space between galaxies, nested inside yet emptier space between clusters. But we are not done yet, because there is a deeper layer to this emptiness that makes everything we have discussed so far look practically crowded by comparison. Even if you counted every star, every galaxy, every cloud of gas and speck of dust between them, you would still be missing most of the universe. In the 1930s, a Swiss astronomer named Fritz Zwicky began studying the Coma cluster, a sprawling group of galaxies roughly 320 million light-years from Earth. Zwicky measured how quickly the galaxies in this cluster were moving. He knew the whole cluster was bound together by gravity, each galaxy tracing out its orbit around a common gravitational center. From the observed velocities of those galaxies, he could calculate how much mass the cluster needed in order to generate enough gravitational pull to hold everything together. Then he did the corresponding inventory of what he could actually see. He counted galaxies, he measured their brightness, he estimated their mass from the light they emitted. And then he hit a wall. The numbers did not even come close to matching. The galaxies he could see were nowhere near massive enough to stay bound. Based on visible matter alone, the Coma cluster should have been flying apart. Its members were moving far too fast for their visible gravity to restrain them. Zwicky calculated that the cluster required approximately 400 times more mass than he could detect. He proposed that the missing mass must exist in some invisible form, some substance that carried gravitational weight but did not emit or reflect light. He called it dark matter. Nobody believed him. The idea sounded ridiculous. Invisible matter that had mass yet refused to interact with light in any way seemed like fantasy. Scientists searched for alternative explanations. Perhaps Zwicky had botched his measurements. Perhaps the galaxies in Coma were not actually gravitationally bound together. Perhaps our understanding of gravity itself broke down at such scales. For decades the problem lingered, but the data would not leave it alone. In the 1970s, an American astronomer named Vera Rubin picked up the thread and began systematically studying the rotation of spiral galaxies. She measured how fast stars orbit the galactic center at various distances from that center. In our solar system, planets follow a strict rule. Those closer to the Sun orbit faster. Mercury sprints while Neptune crawls. This pattern makes physical sense because gravity weakens with distance. The farther you are from the dominant mass, the weaker its pull and the slower your orbital speed. Galaxies should obey the same principle. Stars near the galactic center should whip around quickly, while stars in the outer regions should orbit much more sluggishly. But that is not what Rubin found. She discovered that stars at the outer edges of spiral galaxies orbited just as rapidly as stars near the center, sometimes even faster. It made no sense at all, unless vast quantities of unseen mass existed in those outer regions, generating additional gravitational pull that visible matter alone could not explain. Rubin's results confirmed Zwicky's earlier conclusion with startling clarity. Galaxies hide enormous reserves of unseen mass. The visible stars, gas, and dust account for roughly 15% of a galaxy's total mass. The remaining 85% is something else entirely, something invisible, and it is not confined to galaxies or clusters. Dark matter surfaces every single place astronomers examine, in galactic rotations, in the dynamics of clusters, in the web-like architecture of the cosmos on large scales, in the gravitational bending of light around massive objects, in the intricate temperature patterns etched across the cosmic microwave background. Every independent measurement converges on the same uncomfortable conclusion. Most of the matter in the universe is invisible to us. We cannot see it, we cannot touch it. It refuses to interact with electromagnetic radiation in any meaningful way. It emits no light, absorbs no light, reflects no light. But it unmistakably has mass. It warps space-time. It creates gravity. And it outweighs ordinary matter by a ratio of about 6 to 1. For every kilogram of conventional matter, the protons and neutrons and electrons that compose atoms and therefore stars, planets, and living creatures, there exist approximately 6 kilograms of dark matter. So when we calculated earlier that stars occupy a vanishingly small fraction of cosmic space, we were counting only the ordinary matter. Dark matter takes up even more volume, though it remains invisible to direct observation. Current estimates indicate that dark matter represents about 27% of the universe's total mass energy content. Ordinary matter, the entire inventory of stars and planets and gas and galaxies and human beings, represents only about 5%. That leaves 95% of the universe in forms that we do not genuinely understand. Let's talk about what dark matter actually does, because without it, Galaxies as we know them simply would not exist. The gravity generated by ordinary matter alone is not strong enough to pull primordial gas into the dense, star-forming clumps needed to build galaxies. Here is why. In the early universe, hydrogen and helium gas were spread fairly uniformly throughout space. To form galaxies, this gas needed to collapse gravitationally into dense clouds. But ordinary matter interacts with radiation. As gas clouds collapse and heat up, they radiate energy outward. That radiation carries energy away, yes, but it also produces pressure pushing outward against the collapse. The gas wants to fall inward under gravity, but radiation pressure fights back. This tug-of-war creates a stable balance that is extraordinarily difficult to break with ordinary matter alone. Dark matter solves this problem elegantly. Because dark matter ignores radiation entirely, it feels no radiation pressure at all. It can collapse freely under gravity, unopposed. In the early universe, dark matter performed the first act of construction. It clumped together first, forming halos, spherical clouds of invisible mass bound together by nothing but their own gravity. These dark matter halos carved deep gravitational wells into the fabric of space-time. Ordinary matter, the hydrogen and helium drifting through the young cosmos, then fell into those pre-made wells. Once the gas had been concentrated by dark matter's gravitational scaffolding, it could collapse further and finally give birth to stars. Every galaxy has one of these invisible halos wrapped around it. The visible galaxy, the bright spiral disk or elliptical cloud you can photograph, sits at the center of a much larger, much more massive halo of dark matter. The Milky Way's visible disk spans about 100,000 light-years. Its dark matter halo extends at least 600,000 light-years, and possibly much further. That halo is 6 times larger than the visible galaxy and contains roughly 10 times more mass than all the stars and gas you can see combined. When you look at any image of the Milky Way, you are looking at less than 10% of its total mass. The rest is a vast, invisible shroud surrounding everything. This same structure holds for every galaxy astronomers observe. A visible component woven from stars and gas, and a much larger invisible component made of dark matter. The dark matter dominates the galaxy's gravitational field, shaping how stars orbit and how the galaxy interacts with its neighbors. Astronomers can map these halos by measuring the motions of gas clouds and outlying stars far beyond the visible edges of galaxies. The distribution is highly distinctive. Dark matter is densest at the center and thins gradually outward, but the density falls off much more slowly than the density of visible matter. The stars sit packed into a relatively thin disk. The dark matter drapes across a much larger spherical volume. This difference in spatial distribution is one of the clues that convinced astronomers dark matter must be something fundamentally different from ordinary matter. It cannot merely be cold clouds of ordinary gas or undiscovered planets, or failed stars, or interstellar dust. It is something entirely new. Scientists have built extraordinarily sensitive detectors deep underground, trying to catch the rare moment when a dark matter particle collides with an ordinary atom. The detectors are buried far beneath the surface to shield them from cosmic rays and other sources of interference. Because dark matter barely interacts with ordinary matter, such collisions should be exceptionally rare, but a large enough detector patient enough for long enough might capture one. So far, these experiments have returned essentially nothing definitive. A few ambiguous signals, a few suggestive hints, but nothing confirmed. Other experiments hunt for dark matter at particle colliders like the Large Hadron Collider. The idea is to create dark matter particles directly by smashing ordinary particles together at extreme energies. If dark matter is produced in the collision, it would slip out of the detector invisibly, but its presence would be inferred from missing energy and missing momentum that failed to balance the books. Again, no confirmed detection yet. Physicists have proposed several candidates for what dark matter might be. The leading theoretical contender is called the weakly interacting massive particle, or WIMP. These would be subatomic particles, heavier than protons, that interact with ordinary matter only through gravity and the weak nuclear force. The weak force is responsible for certain kinds of radioactive decay. It operates only across distances smaller than an atomic nucleus and, as the name suggests, it is extremely feeble. If dark matter particles communicate with ordinary matter only through this force, they would be almost impossible to detect directly, yet they would still carry mass and produce gravitational effects. WIMPs would have been forged in the fiery conditions of the early universe when temperatures were high enough to create them. As the cosmos cooled, their production stopped, leaving a specific surviving abundance essentially frozen into existence. Calculations show that if WIMPs exist with the right properties, they would naturally account for about 27% of the universe's mass energy, exactly matching what astronomers observe. That striking coincidence is called the WIMP miracle, and it is why WIMPs have long been the favorite candidate. Yet despite decades of searching, no WIMP has ever been found. This stubborn silence has pushed some physicists toward alternatives. Axions are another candidate, hypothetical particles much lighter than WIMPs, perhaps 1,000,000 times lighter than electrons. Axions were originally proposed to solve a different problem in particle physics, but they could also naturally account for dark matter. If they exist, vast numbers would be required to contribute the observed mass, and because they are so light, they would form structures on different scales than WIMPs would. Primordial black holes are yet another possibility. These are black holes that formed in the earliest moments of the universe not from collapsing stars, but from extreme density fluctuations in the young cosmos. If enough primordial black holes formed within the right mass range, they could play the role of dark matter. They would have mass, they would generate gravity, they would emit no light. But observational constraints make this explanation unlikely. We do not see the gravitational lensing effects that large populations of such black holes would inevitably produce. A minority of physicists have even argued that there is no dark matter at all, and that instead our theory of gravity breaks down at galactic scales. This approach is called modified Newtonian dynamics, or MOND. The idea is that gravity does not follow Newton's inverse square law precisely when gravitational fields become extremely weak. In galaxy-scale fields, gravity might be a little stronger than Newton predicts, eliminating the need to invoke invisible mass. MOND can reproduce galactic rotation curves reasonably well, but it struggles to account for galaxy clusters, gravitational lensing measurements, and the detailed structure of the cosmic microwave background. Most physicists prefer dark matter over modified gravity because dark matter explains a much wider range of observations with greater consistency. But until a dark matter particle is actually detected, modified gravity remains on the table as a possibility. The bottom line is that we know dark matter exists because we can measure its gravitational influence in countless ways. We just do not know what it actually is. It could be WIMPs, axions, primordial black holes, or something nobody has yet imagined. It is one of the deepest unsolved riddles in physics. We are trying to understand 27% of the mass of the universe, and we have no confirmed answer. This mystery somehow makes the emptiness of the cosmos feel even more profound. It is not merely that space is mostly vacant. It is that most of the matter filling the little substance that does exist is invisible and completely unknown. Dark matter is passing through you right at this moment. Billions of dark matter particles are streaming through the Earth, through buildings, through your body every single second. You feel none of it because it does not interact electromagnetically. It does not collide with the atoms in your tissues in any meaningful way. It moves through you as if you are not even there. The only reason we know it exists at all is because we can see its gravitational handprints in galaxies, clusters, and the large-scale architecture of the universe. On human scales, inside our solar system, standing on the surface of Earth, dark matter is completely imperceptible. It is all around you, it has mass, but for any practical purpose it might as well not exist. This is what makes dark matter so strange. It represents the majority of matter in the cosmos. It outweighs ordinary matter 6 to 1. It is essential to galaxy formation. Without it, galaxies would not have formed, stars would not have ignited, planets would not have coalesced, and life would have been impossible. And yet, we cannot see it, cannot touch it, cannot detect it directly, and have no idea what it is. It is as though you discovered that most of your house is built from materials invisible and intangible to you, but which must be there because otherwise the house could not stand. And somehow, impossibly, it gets worse, because then there is dark energy. In 1998, two independent teams of astronomers were studying distant supernovae, the spectacular detonations of dying stars that briefly blaze as bright as entire galaxies. A specific category of supernova, known as Type Ia, proved to be unusually useful because it always explodes with essentially the same brightness. Let me explain why this matters. A Type Ia supernova occurs in a binary star system where two stars orbit each other. One of them is a white dwarf, the dense, compact remnant of a dead star, roughly the mass of the Sun compressed into a body the size of Earth. The other is a normal star still burning hydrogen. The white dwarf gradually pulls material from its companion onto its own surface. That matter accumulates, steadily increasing the white dwarf's mass. When the white dwarf crosses a critical threshold, about 1.4 times the mass of the Sun, something catastrophic happens. This critical mass is called the Chandrasekhar limit, named after Subrahmanyan Chandrasekhar, who calculated it in 1930. At this mass, pressure at the core becomes so intense that carbon fusion suddenly ignites. Carbon fuses into heavier elements in an uncontrolled runaway nuclear reaction. The entire star disintegrates in seconds, releasing as much energy in that brief flash as the Sun will radiate across its entire 10 billion-year lifetime. The critical thing is that this always happens at the same mass. Every Type Ia supernova detonates when it reaches roughly 1.4 solar masses. Because they all explode at the same mass, they all release essentially the same amount of energy and reach roughly the same peak brightness. That consistency makes them what astronomers call standard candles, objects whose intrinsic brightness is already known. If you observe a Type Ia supernova and measure how bright it appears from Earth, you can calculate exactly how far away it must be. The inverse square law is straightforward. A source twice as far away appears 4 times dimmer. 3 times farther, 9 times dimmer. Measure the apparent brightness. Compare it to the known actual brightness, and distance falls right out of the equation. It is one of the most reliable techniques astronomers have for measuring distances to extremely faraway galaxies. In the 1990s, 2 teams decided to use Type Ia supernovae to measure how the universe's expansion rate had changed over cosmic time. The High Z Supernova Search Team and the Supernova Cosmology Project, working independently, using slightly different methodologies, each able to cross-check the other's results. Their goal was simple in principle: determine whether the universe's expansion was slowing down, and if so, by how much. They would find supernovae billions of light-years away, measure their distances, and measure their redshifts. Redshift reveals how fast a galaxy is receding. Light from a receding source is stretched to longer wavelengths, shifted toward the red end of the spectrum. The larger the redshift, the faster the recession velocity. By plotting distance against redshift for many supernovae at many different distances, the teams could reconstruct the expansion history of the universe. They would see how fast the cosmos was expanding at different times in the past. Everyone expected expansion to be slowing down. After the Big Bang, space was blown outward explosively. But matter has mass. Mass generates gravity, and gravity pulls things together. Over cosmic history, gravity should have steadily put on the brakes. The question was not whether expansion was decelerating, but how strongly. Was there enough matter to eventually halt the expansion and trigger a cosmic recollapse, a big crunch? Or would expansion continue forever, but at an ever-decreasing rate? Answering this required exquisitely precise measurements of extremely faint, extremely distant supernovae. Both teams spent years searching, observing, and analyzing. And in 1998, both teams independently announced their findings. The distant supernovae were dimmer than expected. Not by a huge amount, but by a statistically unmistakable margin. Dimmer means farther away. And farther away than predicted meant the universe had expanded more than the prevailing model said it should have. The only way these observations could make sense was if expansion had been speeding up over time instead of slowing down. The universe's expansion is accelerating. This result was completely unexpected. Many physicists initially suspected systematic error, some hidden mistake in the observations or analysis. But both teams, using different methods, found the same result. As more supernovae were observed in the following years, the signal only grew stronger and clearer. The acceleration is real. Something is pushing space itself apart, actively counteracting gravity. We call this something dark energy. But that name is really just a placeholder for our ignorance. We genuinely do not know what it is. The simplest explanation is that dark energy is a fundamental property of space itself. Empty space has energy. This sounds paradoxical, but it is predicted by quantum mechanics. In quantum field theory, empty space is not truly empty at all. It is saturated with quantum fields that permeate everything. These fields possess a ground state, a lowest possible energy level. But even that ground state carries a non-zero energy density. Even perfectly empty space contains a certain amount of energy per cubic meter. This is called vacuum energy, or, in its simplest mathematical form, the cosmological constant. Einstein actually proposed a cosmological constant all the way back in 1917, though for very different reasons. He did not know about quantum fields at the time. He wanted to keep the universe static. Everyone in that era believed the cosmos was eternal and unchanging. But Einstein's equations of general relativity stubbornly predicted that the universe must either be expanding or contracting. Gravity could not allow a static cosmos. To save the traditional picture, Einstein added a term to his equations representing a repulsive force that could balance gravity and keep the universe still. He later called it the biggest blunder of his career, after Edwin Hubble discovered that the universe is, in fact, expanding. Now, 80 years later, observations suggest that the cosmological constant might be real after all, though for reasons Einstein never imagined. If space has a non-zero vacuum energy density, and if that density remains constant as space expands, then as the universe grows larger, the total amount of vacuum energy increases. More space means more vacuum energy, and this energy creates a repulsive gravitational effect, driving space to expand faster. That sets up a feedback loop. Expansion creates more space. More space creates more vacuum energy. More vacuum energy produces faster expansion. The acceleration compounds. That is the simplest picture of dark energy. But there is a colossal problem with this picture, something physicists call the cosmological constant problem. When they calculate what the vacuum energy density should be based on quantum field theory, they get an answer roughly 10 to the 120th power times larger than what we actually observe. That is a 1 followed by 120 zeros. The theoretical prediction and the measured value disagree by 120 orders of magnitude. It is the worst prediction in the history of physics, arguably the single deepest unsolved puzzle in theoretical physics. Either something is catastrophically wrong with our understanding of quantum field theory, or there is some mechanism nearly perfectly canceling out most of the vacuum energy, leaving only a tiny residual that we observe as dark energy. Nobody knows what that mechanism could be, or why the cancellation would be so nearly complete, yet not quite total. Alternative explanations propose that dark energy is not actually constant. It might be a dynamic field that evolves over time. This alternative is called quintessence, named after the ancient philosophical concept of a fifth element beyond earth, water, air, and fire. In quintessence models, dark energy is a field-filling space with an energy density that can vary. The field might have been weaker in the past and might become stronger or weaker in the future. That would change how dark energy affects cosmic expansion over time. Some models even suggest that dark energy could eventually reverse polarity, switching from repulsive to attractive, eventually halting the expansion and causing the universe to collapse in a big crunch. But current observations indicate that dark energy has been essentially constant for billions of years. There is no evidence of it changing, and if it really is constant, the universe will expand forever with ever-increasing acceleration. Whatever dark energy turns out to be, its existence carries profound implications. Dark energy accounts for approximately 68% of the universe's total mass energy content. Dark matter makes up another 27%. Ordinary matter, every single star and planet and galaxy and molecule, contributes only about 5%. Stop and absorb that. We live in a universe where 95% of everything is stuff we fundamentally do not understand. 27% is invisible dark matter we know must exist because we can see its gravitational signature. 68% is invisible dark energy we know must exist because it is driving space itself to accelerate outward. Only 5% is ordinary matter, and even that 5% is spread so thin across such unimaginable distances that in most locations it might as well not be present at all. The universe is dominated by things we cannot explain. That should humble anyone. We take enormous pride in our scientific understanding. We have split the atom, sequenced the human genome, sent probes past the outer planets, detected gravitational waves rippling through space-time. We understand chemistry, electromagnetism, the nuclear forces, quantum mechanics, and relativity. But when we look at the universe as a whole, we must admit that most of it is a mystery to us. We can measure dark matter's effects, but we cannot identify what it is. We can measure dark energy's effects, but we have no accepted theory for what causes it. We are in a position somewhat like ancient astronomers who could track the motions of planets without understanding that planets were worlds, or that Earth was a planet itself. We can measure, predict, and describe, but we do not deeply comprehend, and this lack of understanding makes the emptiness even more disturbing. It is not just that the universe contains a lot of space between things. It is that the little something that exists is largely unknown to us. So the cosmos is empty not only in the sense of having enormous gaps between objects, but also in the sense that almost everything it contains is invisible to direct observation and inexplicable to theory. Only that tiny 5% of ordinary matter is the kind of stuff you can pick up, examine, and name. But there is another layer of emptiness we have not yet addressed: cosmic voids. When astronomers map the distribution of galaxies across large volumes of space, they discover that galaxies are not scattered randomly at all. They cluster into groups, and those groups assemble into still larger structures called superclusters. Superclusters are connected by filaments of galaxies stretching across hundreds of millions of light-years. And between these filaments lie voids, enormous regions where hardly any galaxies exist. Let me describe what this looks like in more concrete terms, because the architecture is remarkable. In the 1970s and 80s, astronomers began creating three-dimensional maps of galactic positions. They recorded not only where galaxies appear on the sky, but also how far away each one is. Distance is inferred from redshift. Light from distant galaxies has been stretched by the expansion of space, shifted toward longer, redder wavelengths. The greater the redshift, the more distant the galaxy. By collecting redshifts for first thousands, then millions of galaxies, astronomers could plot every galaxy's three-dimensional position. What emerged was astonishing. Galaxies are not sprinkled uniformly across space the way stars appear to be on the night sky. They form an elaborate web-like structure of threads and sheets and knots and, most strikingly, vast hollow regions. The first major void was discovered in 1981 by Robert Kirshner and his colleagues, who were surveying galaxies in the constellation Bootes. They expected a roughly uniform distribution. Instead, they found a region with almost no galaxies at all, a sphere roughly 330 million light-years across, containing only about 60 galaxies. This became known as the Bootes void. To appreciate just how empty that is, consider that a typical region of comparable size should contain around 10,000 galaxies. The Bootes void has 60. That is 99.4% fewer galaxies than expected. It is not completely empty. Those 60 galaxies do exist, mostly small dwarf galaxies with a few larger companions. But it is about as close to empty as a region can get, while still being part of the observable universe's structure. If you lived on a planet in a galaxy at the center of the Bootes void, you would look out in every direction and see almost nothing. The nearest significant concentration of galaxies would be more than 165 million light-years away, regardless of which way you turned. For comparison, our nearest large galactic neighbor, Andromeda, sits a mere 2.5 million light-years away. We live in what amounts to a relatively crowded part of the universe. A Bootes void observer would see virtually no galaxies without an extremely powerful telescope. Their sky would be profoundly dark. The cosmic microwave background would still be there, the faint afterglow of the Big Bang filling space with microwave frequency radiation, but in visible light there would be almost nothing. No Milky Way band crossing the sky, because the observer's galaxy would most likely be a small dwarf without a prominent disk. No neighboring galaxies visible to the naked eye. Just darkness. After the Bootes void was discovered, astronomers searched for others and found them absolutely everywhere. Voids are not rare features. They are the dominant architecture of the universe on large scales. Most of the cosmic volume is void. The giant void, also called the Capricornus void, stretches about 1 billion light-years across, containing only a smattering of small, faint galaxies. The Eridanus supervoid is similarly enormous, also roughly 1 billion light-years in diameter. This particular void is interesting because it corresponds to a cold spot in the cosmic microwave background, the relic radiation filling the sky at about 2.7 degrees above absolute zero. That temperature is remarkably uniform across the entire sky, varying by only about 1 part in 100,000. But those tiny variations matter immensely. They represent density fluctuations in the early universe that later grew into galaxies, clusters, and voids. The Eridanus supervoid shows up as a region slightly colder than average in the cosmic microwave background. Photons traveling through it lose energy climbing out of the void's gravitational profile, making them appear colder than the surrounding sky. The observed cold spot is more extreme than models predict even for a void this large. Some physicists have speculated wildly that it might be evidence of something truly exotic, perhaps a collision between our universe and another universe in a multiverse. More likely, it is simply an unusually large void amplified by statistical fluctuation. But it illustrates how strange and extreme cosmic voids can become. The local void is much closer to us, only about 150 million light-years away. It is smaller, about 450 million light-years across, but still impressively empty. The local void is bounded by the local sheet, a structure that includes our local group of galaxies, the Milky Way, Andromeda, and about 80 smaller galaxies. We sit right on the edge of this void, looking straight into it. The dipole repeller is a feature associated with the local void. It is a region of underdense space that appears to be pushing our local group away from it. The effect is gravitational. The void does not actively push because it is empty, but the overdense regions surrounding the void pull matter toward them. From the perspective of matter near the void's edges, this creates an apparent repulsion from the void's center. Matter streams away from voids toward filaments and clusters. This has been confirmed by observations of galactic velocities. Galaxies near voids tend to drift away from the void's center. Galaxies inside filaments tend to flow along the filament toward clusters. The entire structure is in motion, with matter migrating from underdense to overdense regions over hundreds of millions of years. But voids do not fill in over time. They are not temporary features that will eventually disappear as matter trickles back into them. Quite the opposite. Voids are growing. As the universe expands, matter in underdense regions spreads even thinner, while matter in overdense regions becomes more concentrated. The rich get richer and the poor get poorer, cosmologically speaking. Voids expand faster than average because they contain less matter to slow the local expansion. Filaments and clusters expand more slowly, or in some cases even contract, because their higher density generates stronger gravity. So the cosmic web is becoming more pronounced over time. Filaments are getting denser, voids are getting emptier. Eventually, many billions of years from now, most of the universe's matter will be concentrated in isolated clusters of galaxies, separated by gargantuan voids containing almost nothing at all. Dark energy accelerates this process. As expansion speeds up, voids grow even faster. Matter has less time to migrate from voids to filaments before expansion carries it out of reach. So dark energy is actively eroding the universe's structure, stretching it apart, making voids larger and more dominant. The cosmos is evolving toward maximum emptiness. Inside voids, conditions differ profoundly from the regions we inhabit. We live in the local sheet, a relatively dense structure where dozens of galaxies lie within a few million light-years. Our night sky is rich if you know how to look. Star formation continues across the Milky Way and nearby galaxies. New stars are born while old stars die. The cycle goes on. In a void, the environment is harsher for galaxy formation and star formation alike. The few galaxies that exist in voids tend to be small, dim, and low in star-forming activity. Astronomers call them void galaxies. Void galaxies are typically dwarfs, much smaller than the Milky Way. They contain less gas, the raw material of starbirth. They are more isolated, rarely interacting with neighbors, because there are almost no neighbors. Galactic interactions trigger star formation by compressing gas clouds, so void galaxies miss out on this entirely. They evolve slowly, form stars at lower rates, and age with less drama. Some void galaxies are among the most pristine, least altered objects in the universe, essentially untouched for billions of years. They look remarkably similar to how they appeared in the deep past. That makes them scientifically invaluable, like fossils preserving the early epochs of cosmic history. But it also means void galaxies are lonely, isolated, quiet worlds. A civilization arising in a void galaxy would perceive the universe very differently than we do. They would see far fewer galaxies in their sky. They might mistakenly conclude that they live in a much emptier universe than actually exists. Their cosmology would be built on impoverished observations that did not include the rich filamentary structure we see from our privileged vantage. They might still discover the cosmic microwave background and deduce that the universe began in a hot, dense state, but they might never realize that most of the cosmos is organized into filaments and clusters. They might think their lonely void is representative of the whole. It is a sobering thought. Our cosmological understanding depends on where we happen to be located. We are fortunate to live in a relatively crowded pocket where galaxies are plentiful and the cosmic web is clearly visible. If we lived in a void, our cosmology would be poorer, our observations less rich. Location matters, even on cosmic scales. The existence of voids also tells us something important about the early universe. The patterns of filaments and voids we see today originated from minute density fluctuations in the first moments after the Big Bang. Regions that were 1 part in 100,000 denser than average collapsed over billions of years into filaments and clusters. Regions that were 1 part in 100,000 less dense than average became voids. So the structure we see today is the amplified echo of quantum fluctuations from the first instant of cosmic history. Those fluctuations determined where galaxies would form, where voids would empty out, and where we would eventually end up. If the fluctuations had been slightly different, the pattern would be different. Galaxies would occupy different locations. The Milky Way might have ended up in a void instead of a filament. Earth might not exist at all, because the gas cloud that eventually birthed our solar system might have been in a region that never collapsed into a galaxy. We owe our existence to the precise pattern of density fluctuations imprinted on the universe in its first fraction of a second. And that pattern includes voids. Voids are not failures of structure formation. They are an essential part of the cosmic web. You cannot have overdense regions without underdense regions. The matter that flowed into filaments and clusters had to come from somewhere, and it came from the voids. So voids are where the universe sacrificed density in order to build the structures we see. And as the universe continues expanding, voids will grow larger and more dominant until, trillions of years from now, most of the observable universe will be void. The few surviving galaxy clusters will be isolated islands adrift in an ocean of emptiness. Let me explain how expansion actually works in greater detail, because this is central to understanding why scientists cannot stop it. Space itself is expanding. Galaxies are not moving through space away from each other. The space between galaxies is growing. This distinction is subtle but enormous. Imagine dots drawn on the surface of a balloon. As you inflate the balloon, the dots move apart. They are not crawling across the surface. They are being carried by the surface itself as it stretches. Every point on the surface moves away from every other point. There is no center to the expansion on the surface. From the perspective of any given dot, every other dot is receding. The universe works the same way, but in 3 dimensions rather than 2. Space is stretching uniformly in every direction. The farther apart 2 objects are, the faster they appear to recede from each other, because there is more space between them to stretch. This relationship is described by Hubble's law, first discovered by Edwin Hubble in 1929. Hubble measured the distances to galaxies using Cepheid variable stars, pulsating stars whose brightness varies with a predictable period. By measuring the period of pulsation, you can deduce the star's intrinsic brightness. Compare that to its apparent brightness, and distance emerges directly. Hubble also measured the redshifts of those same galaxies, which revealed how fast each one was receding. When he plotted distance against recession velocity, he found a clean linear relationship. Galaxies twice as far away were receding twice as fast. Galaxies 3 times farther were receding 3 times faster. It was revolutionary. Before Hubble, most astronomers assumed the universe was static, eternal, and unchanging. Some galaxies might be drifting toward us, some away, but the cosmos as a whole was going nowhere. Hubble's observations shattered that picture. Every galaxy in every direction was fleeing from us, and the more distant the galaxy, the faster it fled. The only possible explanation was that the universe itself is expanding. Space is growing, carrying galaxies apart on its swelling fabric. The rate of expansion is encoded in a number called the Hubble constant, which relates recession velocity to distance. Current best measurements place the Hubble constant at approximately 43.5 miles per second per megaparsec, where a megaparsec is about 3.3 million light-years. So for every 3.3 million light-years of distance, the recession velocity increases by 43.5 miles per second. A galaxy 10 megaparsecs away recedes at 435 miles per second. A galaxy 100 megaparsecs away recedes at 4,350 miles per second. A galaxy 1,000 megaparsecs away recedes at 43,500 miles per second, and so on. At some distance, the recession velocity reaches the speed of light. In the current universe, this occurs at approximately 14 billion light-years. Beyond that distance, galaxies are receding from us faster than light itself. This does not violate relativity, because the galaxies are not moving through space faster than light. Space itself is expanding faster than light can traverse it. Light leaving a galaxy receding faster than light will never reach us. Even though the light is headed in our direction, space between us is expanding faster than the light can cross it. The light makes forward progress, but the distance it must cover grows faster than it can travel. It is like swimming upstream in a current faster than you can swim. You push forward through the water, but the water carries you backward faster than you can advance, so you move backward overall. Light from these distant galaxies is being carried away from us by cosmic expansion, even as it travels toward us through space. This defines the edge of the observable universe, what cosmologists call the cosmological horizon. Objects beyond this horizon are causally disconnected from us. We can never observe them, never interact with them, never receive any information from them. They presumably exist, but they are forever beyond our reach. And here is the critical point. This horizon is moving inward over time. As the universe continues expanding, and as that expansion accelerates due to dark energy, more and more galaxies cross the horizon and vanish from our view forever. Right now, we can see galaxies about 46.5 billion light-years away in every direction. That is the current radius of the observable universe. But many of those galaxies are already receding from us faster than light. We see them only because the light we are currently receiving left those galaxies billions of years ago, when they were much closer and when expansion was slower. The light they are emitting right now will never reach us. And galaxies that are currently within our observable universe but lying near its edge will eventually cross the horizon as expansion continues. Let's trace what happens to a specific galaxy over deep time. Consider a galaxy currently 10 billion light-years away. That galaxy is receding from us at approximately 435,000 miles per second. That is more than twice the speed of light. We can see this galaxy because we are receiving light that left it 10 billion years ago, when it was much closer and expansion was slower. But that galaxy is now crossing, or may have already crossed, our cosmological horizon. In the far future, light from that galaxy will become so profoundly redshifted that it becomes undetectable. The wavelengths will stretch from nanometers to meters to miles to eventually light-years in length. The photons will carry so little energy that they might as well not exist at all, and new light leaving that galaxy will never reach us. From our perspective, the galaxy will fade and vanish. Now consider galaxies that are currently closer, say 5 billion light-years away. These are receding more slowly, perhaps 217,000 miles per second. Still faster than light, but less extreme. We can observe them comfortably with modern telescopes. But over time, as expansion continues and accelerates, these galaxies too will recede faster and faster. Eventually, they also cross the horizon. The observable universe is shrinking from the outside inward. The most distant galaxies disappear first, then slightly closer ones, then closer still. Given enough time, only our local group will remain visible. But there is a limit to this shrinkage because gravity holds bound structures together. Objects that are gravitationally bound do not participate in cosmic expansion. The Milky Way and Andromeda are gravitationally locked in mutual approach, actually moving toward each other on a collision course. The expansion of space has no effect on this relationship because gravity is stronger than expansion on this scale. Our local group contains roughly 80 galaxies, all gravitationally connected. They will eventually merge into a single large elliptical galaxy over the next several billion years. This merged galaxy will survive cosmic expansion because it is held together by its own gravity. Similarly, our local supercluster, the Laniakea supercluster, contains about 100,000 galaxies. Gravity binds this structure loosely. Some parts of it may stay connected across cosmic time. But beyond the supercluster scale, expansion wins decisively. Galaxy clusters not bound to our supercluster are being swept away. The Virgo cluster, the Fornax cluster, the Coma cluster, all of them are receding from us. Over tens of billions of years, they will cross the horizon and vanish. Eventually, observers in what remains of our local group will look up at their sky and see only their own merged galaxy, plus perhaps a few satellite dwarfs still bound to it. Everything else will be gone, carried beyond the horizon by accelerating expansion. The cosmic microwave background will also fade away. Right now, the CMB is detectable as microwave frequency radiation at 2.7 degrees above absolute zero. But as space expands, this radiation is stretched to longer wavelengths and lower energies. Over trillions of years, it will be redshifted into radio waves, then into even longer wavelengths. Its effective temperature will drop below 1 degree Kelvin, then below 1/10 of a degree, inching toward absolute zero. Eventually, it will be so diffuse and so low energy that no conceivable technology could detect it. The CMB, the most direct evidence we currently have of the Big Bang, will be erased by expansion. Future civilizations will be unable to observe it. They will not know that the universe had a hot, dense beginning. They might develop physics and chemistry and understand how stars and planets form, but cosmology as we know it would be impossible for them. They would have no way to discover the Big Bang, no way to measure cosmic expansion, no way to infer the universe's history. They would be observationally isolated, trapped in a single galaxy or small group, with no evidence that anything else ever existed. This has led some physicists to wonder what we might already be missing. Are there aspects of cosmology we simply cannot access because they have already been erased by expansion? Were there structures or events in the very earliest universe for which all traces have been redshifted beyond detection? Possibly. We can observe back to the cosmic microwave background, which formed about 380,000 years after the Big Bang. Before that, the universe was opaque to light, too hot and dense for photons to travel freely. We have no direct optical observations of the first 380,000 years. We can infer what happened using physics and theoretical modeling, but direct observation is impossible. Could there have been interesting structure or phenomena during that era that left no observable trace? We may never know. Similarly, there might be structures or phenomena lying beyond our current cosmological horizon that we have no way to detect. The observable universe might be only a tiny fraction of the total universe. Everything beyond our horizon is unknowable to us. This is humbling. We can map and measure and understand the observable universe, but we must accept that this might be only a small sample of everything that exists, and that sample is shrinking over time as more objects slip beyond the horizon. The universe we can observe is contracting while the total universe continues to grow. Our window on reality is closing. In this context, we are extraordinarily fortunate to exist at this particular moment, when the universe is still observable, when distant galaxies are still visible, when the CMB is still detectable, when we can still measure expansion and infer the Big Bang. A few trillion years from now, none of this will be possible. Future civilizations will inherit a lonelier, darker cosmos, with far less information available to them. This raises profound questions about our place in cosmic history. Are we early or late in the universe's timeline? The universe is approximately 13.8 billion years old. Stars will keep forming for at least another 100 trillion years, possibly much longer. So we are only about 0.01% of the way through what cosmologists call the stelliferous era, the age of stars. We are incredibly early. Most stars that will ever exist have not yet formed. Most planets have not yet coalesced. Most opportunities for life have not yet arisen. We might be among the first civilizations to emerge in the universe. Or we might not be. Perhaps intelligent life is common, and we are utterly ordinary. Perhaps it is rare, and we are unusual. We do not know. But we do know that we exist at a time when the universe is maximally observable. In the deep past, it was too hot and dense for complex structure. In the deep future, it will be too empty and dark for cosmology. Right now, we are in the sweet spot. And that is not a coincidence. Life requires particular conditions. Stars, planets, stable environments, billions of years of evolutionary time. These conditions exist during the stelliferous era, when the universe has cooled enough for structure but has not yet expanded so dramatically that structure is isolated into unreachable fragments. So intelligent life, wherever it arises, will tend to find itself in this same window. This is a form of selection bias called the anthropic principle. We observe the universe to be in a life-friendly state because we could not exist to observe it otherwise. If the universe were too young, too hot, too dense, we would not be here. If it were too old, too cold, too empty, complex structures like us probably could not form. Our existence at this particular moment is not random. It is a consequence of the conditions required for observers to emerge. But even within the stelliferous era, there is a narrower window for cosmology. Right now we can see distant galaxies and the CMB. In 1 trillion years, distant galaxies will be gone, and the CMB will be faint. In 10 trillion years, cosmology will be nearly impossible. So there is a brief period, cosmologically speaking, when the universe is both observable and inhabited by intelligence. We are living inside that period right now. And what we are observing is a universe in the process of becoming emptier. Let's return to the present and ask why the universe is expanding at all in the first place. Why is space stretching? Why are galaxies scattered so thinly? Why is dark matter spread so thin? The answer lies in the early universe and the processes that created all the structure we see today. In the first instance after the Big Bang, the universe was incredibly dense and hot. All the matter and energy that would eventually form galaxies, stars, planets, and us was crammed into an unimaginably tiny volume. The entire observable universe, which today stretches 93 billion light-years across, was compressed into something smaller than an atom. Temperatures exceeded anything we can create or realistically imagine. 1 second after the Big Bang, the temperature was approximately 10 billion degrees Kelvin. 1 millisecond after the Big Bang, 1 trillion degrees. 1 microsecond after the Big Bang, 10 trillion degrees. Go earlier still, and the temperature climbs to energies where our current physics breaks down. At these temperatures, matter as we know it could not exist. No atoms, no molecules, not even protons or neutrons. Just a seething soup of fundamental particles and radiation, quarks and gluons and electrons and photons, colliding violently in an incomprehensibly hot, dense plasma. This state lasted only a tiny fraction of a second. As the universe expanded, it cooled rapidly. At about 1 microsecond old, quarks combined into protons and neutrons. At about 3 minutes old, protons and neutrons combined into the first atomic nuclei, mostly hydrogen and helium. At about 380,000 years old, the universe cooled enough for electrons to combine with nuclei, forming the first complete atoms. This moment is called recombination. Before recombination, the universe was opaque to light because photons constantly scattered off free electrons. After recombination, with electrons bound into atoms, photons could travel freely. The universe became transparent. The photons that were liberated at recombination are what we see today as the cosmic microwave background. They have been traveling through space for 13.8 billion years, redshifted by expansion from visible light down to microwaves. The CMB provides us with a snapshot of the universe at age 380,000 years, and that snapshot shows something remarkable. The universe was astonishingly uniform at that time. The temperature varies by only about 1 part in 100,000 across the entire sky. Some regions were slightly hotter, slightly denser than average. Other regions were slightly cooler, slightly less dense. But these variations were minuscule compared to the differences we observe today. This uniformity is puzzling. How could regions of space, billions of light years apart, have nearly identical temperatures? They could not have been in thermal contact, could not have exchanged heat to equilibrate. Light has not had time to travel between them even now, let alone in the early universe. The solution is called cosmic inflation. This is the idea that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. Space grew faster than light, doubling in size many times over in an incomprehensibly brief interval. Different models of inflation predict different details, but the basic picture is that in roughly 10 to the negative 32nd power seconds, the universe expanded by a factor of at least 10 to the 26th power. That is roughly 87 doublings, crammed into a moment so short it borders on meaningless to human comprehension. For comparison, there have been roughly 10 to the 18th power seconds in the entire age of the universe. The inflation period was 10 to the negative 32nd power seconds. That is a million trillion times shorter than the universe's current age. And in that absurdly brief moment, space expanded by a factor of at least 100 million trillion. The observable universe of today, 93 billion light-years across, was smaller than a proton before inflation. After inflation, it was roughly the size of a grapefruit or basketball, depending on the model. Then, inflation ended and normal expansion took over, gradually increasing in scale over the next 13.8 billion years to reach its current size. Why did inflation happen? We do not know for certain. The leading explanation is that it was driven by a field called the inflaton field, which filled all of space. This field possessed potential energy, like a ball perched on top of a hill. The ball wants to roll down to the bottom, but it is temporarily stuck at the top. Similarly, the inflaton field was trapped in a high-energy state, and while it was stuck, its energy caused space to expand exponentially. Eventually, the field rolled down into a lower energy state. Inflation ended, and the field's energy converted into particles and radiation, reheating the universe. This reheating created all the matter and energy we see today. In a sense, inflation borrowed energy from empty space, used it to inflate space exponentially, and then converted it into matter when the process ended. Inflation solves several otherwise mystifying puzzles in cosmology. It explains why the universe is so uniform. Before inflation, the entire observable universe was a tiny patch, small enough to have been in thermal equilibrium. All parts were in contact, exchanging heat, reaching the same temperature. Inflation then stretched this tiny uniform region to enormous size. The uniformity was preserved, stretched out along with space. That is why the CMB looks so uniform today. Inflation also explains why the universe is geometrically flat. General relativity allows three possible geometries. Positive curvature like the surface of a sphere, where parallel lines eventually converge. Negative curvature like the surface of a saddle, where parallel lines diverge. Or flat like a plane, where parallel lines stay parallel. Measurements show the universe is flat, to remarkable precision. But flatness is unstable. Any tiny initial curvature would be amplified by expansion over time. For the universe to be flat today, it must have been preposterously close to exactly flat at the beginning. This seemed like an implausible fine-tuning. Inflation resolves it, because exponential expansion stretches out curvature. Any initial curvature gets inflated away, flattened nearly to zero. The observable universe becomes such a tiny patch of something much larger that any curvature is undetectable within it. It is like zooming in on the surface of a sphere. At small scales, the sphere looks curved, but zoom in far enough, and any small patch looks flat. Inflation zoomed in on the universe, making the observable region a tiny patch of something vastly greater. But inflation's most crucial contribution for our purposes is that it seeded all the structure we see. The inflaton field was subject to quantum fluctuations. At quantum scales, fields never have precise values. They fluctuate randomly due to the Heisenberg uncertainty principle. Normally, these fluctuations are microscopic and irrelevant. But during inflation, quantum fluctuations got stretched to cosmic scales. A fluctuation smaller than a proton was inflated to the size of a galaxy or larger. These stretched quantum fluctuations became the density variations of the early universe. Regions where the inflaton field happened to have slightly more energy became slightly denser after inflation ended. Regions with slightly less energy became slightly less dense. These density variations were imprinted on the matter and radiation when the inflaton field decayed, and they are what we observe today as the temperature variations in the CMB. 1 part in 100,000 differences in density may not sound like much, but gravity amplifies density differences over time. A region slightly denser than average generates slightly more gravity, pulling in nearby matter, which increases its density, which strengthens gravity further, which attracts even more matter. Positive feedback. Over hundreds of millions of years, regions that began only 1 part in 100,000 denser collapsed into the first galaxies. The first stars formed within these galaxies, probably about 100 million years after the Big Bang. These were massive stars, hundreds of times the mass of the Sun, burning fiercely and dying young in supernova explosions that scattered heavy elements into space. Later generations of stars formed from gas enriched with these heavy elements. Galaxies grew by steadily accreting more gas and forming more stars. They also grew by merging with other galaxies. The cosmic web structure emerged as matter flowed from underdense regions toward overdense regions. Filaments formed connecting galaxy clusters. Voids emptied out as matter drained toward filaments. By about 1 billion years after the Big Bang, the large-scale structure was beginning to resemble what we see today. Galaxies, clusters, filaments, voids. But here is the key point. The initial density variations were incredibly small, only 1 part in 100,000. If they had been exactly zero, perfectly uniform, no structure could ever have formed. Gravity would have had nothing to amplify. Matter would have remained uniformly spread out as space expanded. No galaxies, no stars, no planets, no life. Just a thin gas of hydrogen and helium growing ever thinner as the cosmos swelled. But equally, if the density variations had been much larger, say 1 part in 1,000 instead of 1 part in 100,000, gravity would have been too strong. Dense regions would have collapsed too quickly and too violently. Instead of forming galaxies, they would have collapsed directly into black holes. The universe would have been riddled with black holes soon after the Big Bang, with no opportunity for stars or planets to form. So the amplitude of the density fluctuations had to be just right. Large enough for structure to emerge, small enough for that structure to form gradually, allowing stars and galaxies to develop rather than just black holes. This fine-tuning is part of why the cosmos is expanding into the kind of emptiness we now witness. If density fluctuations had been larger, more matter would have clumped together. Galaxies would be more common and closer to each other. The space between them would contain less emptiness. But then conditions would not have been right for star formation and life. If density fluctuations had been smaller, less matter would have clumped together. Galaxies would be rarer, scattered farther apart. Space would be even emptier than it is. And again, conditions would not have been right for star formation and life. We observe the universe to have this particular level of structure because it is the level compatible with our existence. Too full and black holes dominate. Too empty and galaxies never form. Just right and we get galaxies and stars and planets and us. This is another manifestation of the anthropic principle. The universe's expansion rate and structure are consequences of the conditions required for observers to exist. So when we ask why space is stretching as it does, part of the answer is that it could not be much different and still produce structures like us. But there is more to the story. The density fluctuations set up the initial distribution of matter. Expansion determines how that matter disperses over time, and this is where dark energy becomes crucial. In a universe without dark energy, containing only matter and radiation, expansion would gradually slow down over time. Gravity would work to pull everything back together. The universe might eventually stop expanding and recollapse in a big crunch. Or it might expand forever but at an ever-decreasing rate, asymptotically approaching zero expansion. In either case, the relative distances between structures would remain roughly constant or decrease. Galaxies that are close now would stay close or grow closer. The cosmic web would persist or even strengthen over time as gravity pulled filaments and clusters together. But we do not live in that universe. We live in a universe dominated by dark energy. And dark energy causes expansion to accelerate. That changes everything. Instead of gravity gradually winning, pulling structures together, expansion is winning, pulling structures apart. The cosmic web is being stretched. Filaments are thinning. Voids are growing. And the process is accelerating. Dark energy's density appears to be constant or nearly constant as space expands. This means that as the universe grows larger, there is more total dark energy. Meanwhile, the density of matter decreases as space expands because the same amount of matter is spread over a larger volume. So dark energy's influence grows stronger relative to matter's influence as time passes. In the early universe, matter dominated. The cosmos was dense enough that matter's gravity overwhelmed dark energy's repulsive effect. Expansion was decelerating, slowing down under matter's gravitational pull. This allowed structures to form. Overdense regions could collapse because expansion was not yet too fast. Matter had time to flow from underdense to overdense regions, weaving the cosmic web. But about 5 billion years ago, dark energy began to dominate. The universe had expanded enough that matter became sufficiently dilute. Dark energy's constant density meant it now contributed more to the total energy density than matter did. Expansion began accelerating, and it has been accelerating ever since. This acceleration is gradually destroying structure. Objects not bound by gravity are being pushed apart faster and faster. In the far future, the universe will be much emptier than it is today. Most matter will be concentrated in isolated galaxy clusters or individual merged galaxies, separated by voids billions or trillions of light years across. The cosmic web will be gone, stretched out of existence. Eventually, over timescales beyond casual comprehension, dark energy might overcome even gravitational binding. There is a speculative scenario called the Big Rip, in which dark energy's density increases over time rather than remaining constant. If this happens, expansion accelerates more and more dramatically until it tears apart even bound structures. First, galaxy clusters dissolve, then individual galaxies, then stellar systems, then planets, then molecules, then atoms, then atomic nuclei. Everything gets ripped apart by exponentially increasing expansion. The universe ends not in fire or in ice, but in being torn to pieces at every scale. This is speculative, and most physicists do not think it is likely. But we cannot rule it out, and its mere possibility is chilling. More likely, dark energy's density remains constant, and the universe simply expands forever with constant acceleration. This leads to heat death, a cold, dark, empty future where all structures have dissolved and all energy has dissipated. But that fate lies trillions of years away. For now, we live in a universe that is expanding but not yet maximally empty, where structure exists but is gradually dissolving, where galaxies shine but are slowly being isolated from each other by expanding space. And it is getting worse. As the universe continues to expand and dark energy drives accelerating expansion, structures are being pulled apart. Galaxies that are not gravitationally bound are receding from each other faster and faster. Galaxy clusters are becoming more isolated. Superclusters are dissolving. The cosmic web is being stretched, with filaments thinning and voids expanding. Eventually, over timescales of hundreds of billions or trillions of years, even gravitationally bound structures might be affected. If dark energy continues to dominate and its density remains constant or grows, it could eventually overcome gravity on smaller and smaller scales. First, it would dissolve superclusters, then galaxy clusters, then galaxy groups. Eventually, it could even tear apart individual galaxies, pulling stars away from each other. In the most extreme scenario of the Big Rip, dark energy would eventually overwhelm the forces holding atoms together. Molecules would be torn apart, then atoms, then atomic nuclei, then even the quarks inside protons and neutrons. The universe would be shredded at every scale from largest to smallest, until nothing remained but isolated particles spreading through infinite space. This is speculative. We do not know whether dark energy will remain constant, increase, or decrease over time. But current evidence suggests it is at least constant, which means the universe will continue expanding forever. Structures will continue dissolving, and emptiness will continue growing. The universe's fate appears to be heat death. Let me explain what heat death means in detail, because it is both the most likely ultimate fate and one of the most profound concepts in physics. Heat death does not mean the universe becomes hot. It means the universe reaches thermal equilibrium, a state where energy is evenly distributed and no more work can be done. Picture a cup of hot coffee sitting in a cool room. The coffee is hotter than the surrounding air. Heat flows from coffee to room. Over time, the coffee cools and the room warms slightly until they reach the same temperature. At that point, no more heat flows. The system has reached thermal equilibrium. The coffee and room still contain energy, but that energy is now evenly distributed. No temperature differences, no gradients, no way to extract useful work from the system. The universe is heading toward the same fate on an incomprehensibly larger scale and across an unimaginably longer time span. Right now, the universe is nowhere near equilibrium. Stars are hot. Space is cold. Galaxies are dense. Voids are empty. There are gradients everywhere. Differences in temperature, density, and energy. These differences allow things to happen. Stars burn, planets orbit, galaxies evolve, life exists. All of it depends on being out of equilibrium, on having energy concentrated in some places and not others. But the second law of thermodynamics says entropy always increases in a closed system. Entropy is a measure of disorder, of how spread out energy is. High entropy means energy is evenly distributed. Low entropy means energy is concentrated. The universe began in a low entropy state, with energy concentrated in the Big Bang. As time passes, entropy increases. Energy spreads out. Differences fade. This process continues until everything reaches equilibrium. When that happens, the universe will be in a state of maximum entropy, maximum disorder, maximum emptiness, in a sense, because no concentrated structures remain. Let's trace this process over deep time. We are currently about 13.8 billion years into the universe's history. For the next 100 trillion years or so, stars will continue forming from gas and galaxies, though not at the rate they do now. Star formation is already declining, and it will continue to slow as gas is consumed or ejected from galaxies. But there is enough gas remaining that small red dwarf stars, the longest-lived type, will keep forming for at least 100 trillion years. So for the next 100 trillion years, the universe will still contain stars shining, planets orbiting, potentially life evolving. This is the stelliferous era, the age of stars, and we are about 0.01% of the way through it. Most of it lies ahead. But eventually the gas runs out or becomes too dispersed for new star formation. By about 100 trillion years from now, star formation will essentially cease. From that point forward, only existing stars remain, slowly burning out. Red dwarfs, the smallest stars capable of sustaining fusion, live for trillions of years. Some born today will still be shining 100 trillion years from now. But one by one, they exhaust their hydrogen fuel and die. A red dwarf becomes a white dwarf, a hot, dense remnant about the size of Earth containing the star's leftover mass. White dwarfs do not burn fuel. They simply cool down gradually over trillions of years, radiating away their remaining heat. By about 10 to the 15th power years from now, 10 quadrillion years, all stars will have died. No more fusion, no more starlight. The universe enters what is called the degenerate era, named after the quantum degenerate matter that constitutes white dwarfs. At this point, the universe contains mostly white dwarfs, neutron stars from past supernovae, and black holes from collapsed massive stars. There are also brown dwarfs, failed stars that never ignited fusion, slowly cooling. And there are planets no longer orbiting stars, drifting through space or orbiting white dwarfs. Everything is dark and cold. White dwarfs and neutron stars still glow faintly from residual heat, but that heat gradually radiates away. Eventually, over timescales of 10 to the 30th power years, all these objects cool to near absolute zero. They become black dwarfs, cold, dark remnants with no internal heat. During this time, another process is at work. Gravitational interactions between objects and galaxy remnants gradually eject most objects into intergalactic space. When two objects pass near each other, they exchange momentum gravitationally. One speeds up, one slows down. The one that speeds up might achieve escape velocity and get flung out of the galaxy. The one that slows down falls deeper into the galaxy's gravitational potential. Over trillions of years, this process called gravitational slingshot ejects about 90% of objects from galaxies. They drift off into intergalactic space, isolated, cooling, never to interact with anything again. The remaining 10% fall toward the galaxy's center, where they either collide and merge or orbit the central supermassive black hole. By about 10 to the 30th power years, galaxies have largely evaporated. Most stellar remnants are isolated in intergalactic space. A few have merged or been captured by black holes. And speaking of black holes, they are the longest-lived objects in the universe. White dwarfs cool but do not disappear. Black dwarfs just sit there forever, unless something happens to them. Black holes, paradoxically, eventually evaporate. This was discovered by Stephen Hawking in 1974. Hawking showed that quantum effects near a black hole's event horizon cause it to emit radiation. Here is how it works. In quantum field theory, empty space is saturated with quantum fluctuations, where particle-antiparticle pairs briefly pop into existence before annihilating each other. Near a black hole's event horizon, these fluctuations can be separated. One particle falls into the black hole, its partner escapes. From outside, it appears the black hole is emitting particles. This radiation carries away energy, which must come from the black hole's mass via E equals mc squared. So the black hole slowly loses mass. It evaporates. The rate of evaporation depends on the black hole's mass. Larger black holes evaporate more slowly than smaller ones. A black hole with the mass of the Sun would take about 10 to the 67th power years to evaporate completely. That is 10 million trillion years. A timescale so vast it is effectively meaningless. For comparison, the universe's current age is only about 10 to the 10th power years. Supermassive black holes at galactic centers, with masses millions or billions of times the Sun's, take even longer. A billion solar mass black hole evaporates in roughly 10 to the 100th power years. 10 duotrigentillion years. There is no physical intuition for a timescale this vast. The entire history of the universe from the Big Bang until now is less than a single instant compared to these spans. But eventually, even supermassive black holes evaporate. Their final moments are dramatic. As a black hole loses mass, its temperature rises and it radiates faster. The evaporation accelerates. In its last second, a black hole releases as much energy as billions of nuclear bombs. A final flash of gamma rays, and then nothing. The black hole is gone, converted entirely into radiation that spreads into space, so by about 10 to the 100th power years, all black holes have evaporated. What remains? Isolated black dwarfs, drifting through expanding space. Perhaps some neutron stars and white dwarfs that were never captured by black holes. Photons, the light and heat once radiated by everything that ever shone, now redshifted to unimaginable wavelengths and energies near zero. Neutrinos left over from old nuclear reactions and ancient supernovae. And dark matter, whatever it is, still present but spread incredibly thin. Everything is cold, approaching absolute zero. Everything is isolated, separated by distances that dwarf current intergalactic scales. The observable universe at this point would be vastly smaller than it is now, because accelerating expansion has pushed almost everything beyond the cosmological horizon. An observer, if any could exist, would see only the immediate local vicinity, maybe a few nearby black dwarfs within a trillion light-years. Everything else lies beyond detection. But we are not quite done yet, because there is one more process that might occur: proton decay. In the standard model of particle physics, protons are stable. They do not decay spontaneously. An isolated proton could in principle exist forever, but some theories beyond the standard model, particularly grand unified theories, predict that protons do decay, just extremely slowly. If they do, their lifetime is at least 10 to the 34th power years. That is the current experimental lower bound. We have searched for proton decay in large detectors containing trillions of protons and have not seen any decay in decades of observation. This places constraints on how fast protons can decay, but it is still possible that they decay with a lifetime of 10 to the 36th or 10 to the 40th power years. We simply would not have detected it yet. If protons decay, then all matter eventually breaks down. Black dwarfs are made of atoms, which are made of protons, neutrons, and electrons. Neutrons outside atomic nuclei are unstable, decaying in about 15 minutes. But neutrons inside nuclei are stable, held together by the strong nuclear force. However, if protons decay, neutrons will also decay shortly afterward because the nucleus becomes unstable. So a black dwarf would slowly dissolve as its protons decay one by one over timescales of 10 to the 40th power years. Every black dwarf would eventually vanish, converted into lighter particles like positrons, neutrinos, and photons. These particles would spread into space, contributing to the background radiation. At this point, matter in the conventional sense no longer exists. No atoms, no nuclei, no stellar remnants. Just a thin soup of photons, neutrinos, electrons, positrons, and whatever dark matter is, all spread across infinite expanding space at temperatures incomprehensibly close to absolute zero. The universe has reached heat death, maximum entropy, complete thermal equilibrium, no differences anywhere, no gradients. No concentrated energy. Nothing can happen, because there is no energy differential to power any process. This is the ultimate fate of the universe in the most likely scenario. Not a dramatic ending. No big crunch. No big rip. Just a slow, inevitable fade into cold, dark, empty equilibrium. And here is the profound part. From a certain perspective, the universe appears to exist for about 10 to the 40th power years. That is the time scale by which proton decay finishes dissolving everything. But from the perspective of the universe itself, from initial singularity to final equilibrium, the vast majority of that time is spent in the equilibrium state. The interesting part, the part with structure and stars and galaxies and life, is only the opening flicker, 10 to the 14th power years of star formation, 10 to the 30th power years of stellar remnants cooling, 10 to the 100th power years of black hole evaporation. Then infinity, or near infinity, in the equilibrium state. The entire history of the universe that we can relate to, everything that has ever happened or will happen that we would consider significant, occurs in the first 10 to the 100th power years. After that, it is just empty space expanding forever. No more events, no more changes, no more history. The universe does not end so much as it stops doing anything interesting. Even those timescales, 10 to the 40th power years or 10 to the 100th power years, are vanishingly brief compared to eternity. If the universe truly exists forever, and there is no reason in this scenario to think it will not, then almost all of time is spent in that final equilibrium state. The era of structure and complexity, the era in which we exist, is an infinitesimally brief flicker at the very beginning. We exist in the first moment after the Big Bang, cosmologically speaking. A moment of disequilibrium before the universe settles into eternal equilibrium. This is what makes the expansion terrifying. It is not just that space is stretching now, it is that emptiness is the final state, the state that will persist forever. Fullness, structure, complexity, all of them are temporary. Emptiness is permanent. But we are not there yet. We live in what is called the stelliferous era, the age of stars. This era began a few hundred million years after the Big Bang, when the first stars ignited. It will continue for trillions of years as stars are born, live, and die. We are about 1% of the way through this era, possibly even less depending on how long star formation can continue. The universe is approximately 13.8 billion years old. Stars will continue forming for at least another 100 trillion years, possibly much longer in the smallest red dwarfs. So while the universe is already mostly empty, it is actually in one of its fullest states relative to what came before and what will come after. There are more stars and galaxies now than there were a billion years ago. And there will be more stars in the future, formed from gas in existing galaxies, until that gas is exhausted or scattered by expansion. This moment in cosmic history is uniquely rich, uniquely complex, uniquely full of structure. And the most remarkable structures of all are the galaxies themselves. Galaxies should not exist. Not in the way they do. Let me explain why this is such a profound mystery. When you look at a galaxy, you are seeing hundreds of billions of stars held together by gravity, orbiting a common center in a relatively organized configuration. Spiral galaxies have beautiful spiral arms where young stars are being born. Elliptical galaxies are smooth, featureless clouds of old stars. Irregular galaxies are chaotic, but still coherent structures. All of this implies that galaxies are stable, that their stars have had time to settle into organized orbits, that their structures can persist for billions of years. But the universe is only 13.8 billion years old, and galaxies formed relatively early, within the first billion years after the Big Bang. Some of the oldest galaxies we observe with the James Webb Space Telescope appear to be massive, well-formed galaxies existing only a few hundred million years after the Big Bang. This is shockingly fast. Gravity works slowly. To form a galaxy, you need gas to collapse under gravity into a dense cloud. That cloud must then fragment into smaller clouds that become stars. Those stars orbit the galaxy's center, their orbits shaped by the galaxy's total mass distribution. Over many orbits, stars interact gravitationally, their orbits evolve, and the galaxy settles into a stable configuration. This should take many orbital periods. In the Milky Way, an orbit around the galactic center at the Sun's distance takes about 230 million years. Stars closer to the center orbit faster. Stars farther out orbit slower. It should still take many orbits for a galaxy to settle down. 10 orbits. 20, perhaps 50. That would be 5 to 10 billion years. Yet we see well-formed galaxies existing only a few hundred million years after the Big Bang. They seem to have formed almost instantly on cosmic timescales. How? Part of the answer is dark matter. Dark matter does not interact with radiation, so it can collapse rapidly without being slowed by radiation pressure. Dark matter halos form first, carving out gravitational wells. Ordinary matter falls into those wells, concentrated by the dark matter's gravity. This dramatically accelerates galaxy formation. Without dark matter, galaxies would take much longer to assemble, possibly so long that the window for star formation would close before galaxies stabilized. But even with dark matter, mysteries remain. Why are spiral galaxies so organized? Spiral arms are patterns where star formation is enhanced by density waves traveling through the galactic disk. Gas clouds compress when they enter a spiral arm, triggering star formation, creating bright young stars that define the arm's visible structure. But spiral structure should be unstable. Differential rotation, where inner parts of the disk orbit faster than outer parts, should wind spiral arms tighter and tighter until they disappear. This is called the winding problem. Yet spiral galaxies maintain their spiral structure for billions of years. The leading explanation is that spiral arms are not material structures at all. They are density waves, like sound waves or water waves. The pattern moves, but the material does not. Stars and gas flow in and out of spiral arms as they orbit, but the arms themselves persist as patterns in the density distribution. This works mathematically, but it requires specific conditions in the galaxy's disk. The disk needs to be the right mass, the right size, with the right distribution of stars and gas. Too massive or too light, and spiral structure cannot survive. Why do so many galaxies satisfy these conditions? We do not fully know. Another mystery is galactic rotation curves. When astronomers measure how fast stars orbit at various distances from the galactic center, they find something unexpected. In the outer regions of galaxies, stars orbit much faster than they should, based on visible matter alone. This is the primary evidence for dark matter. But the distribution of dark matter needed to explain the rotation curves is highly specific. Dark matter forms a roughly spherical halo around each galaxy with a particular density profile, dense at the center, gradually thinning outward. This profile, called the NFW profile after the physicists who discovered it, emerges naturally from computer simulations of dark matter collapse. But why does nature so consistently produce this particular distribution? And why does the dark matter halo match the visible galaxy so precisely in ways that produce stable rotation curves? It is almost as if dark matter knows what the visible galaxy is doing and adjusts itself to maintain stability. Dark matter does not, of course, know anything. It interacts purely through gravity. But the fact that these two components, dark matter and ordinary matter, work together so seamlessly to create stable galaxies is remarkable. It suggests something deep about how structure forms in the universe, something we do not yet fully understand. There is also the puzzle of galaxy masses. Galaxies come in an enormous range of sizes, from dwarf galaxies with 10 million stars to giant ellipticals with 10 trillion stars. That is a factor of 1,000,000 in mass. Why this particular range? Why not galaxies with only 1,000 stars, or galaxies with a quadrillion? The answer seems to be that smaller structures cannot hold together against various disruptive processes. Supernova explosions, stellar winds, radiation pressure from young stars. All of these can blow gas out of small galaxies. If a galaxy is too small, it loses its gas and cannot form new stars. It fades away or gets absorbed by a larger neighbor. On the large end, there seem to be limits to how big galaxies can grow. The largest galaxies form at the centers of massive galaxy clusters through mergers. They are enormous, containing trillions of stars, but even they have limits imposed by the amount of matter available in their region and by the expansion of the universe, which prevents more distant matter from falling in. So the range of galaxy masses we observe is shaped by physical processes that favor certain scales over others. But the details of why galaxies exist in exactly the forms they do, with the properties they have, remain active areas of research. Computer simulations can produce galaxies that resemble real ones, but only with careful tuning of parameters, and observations keep revealing surprises. The James Webb Space Telescope is finding massive galaxies in the early universe that should not exist according to our models. They are too massive, too well-formed, too quickly after the Big Bang. Either our models are missing something important about galaxy formation, or there is genuinely new physics we do not yet understand. This is exciting for astronomers because it means we are still discovering how the universe works. But it also means galaxies are even more remarkable than we once thought. They are not inevitable structures that form easily. They are delicately balanced systems whose existence depends on multiple factors being just right. Dark matter providing gravitational scaffolding. Initial density fluctuations of just the right amplitude. Star formation processes converting gas into stars at just the right rate. Feedback from supernovae and black holes regulating how much gas remains. Mergers and interactions between galaxies redistributing matter. All of this has to work together to produce the galaxies we observe. Change any one factor significantly, and galaxies would look very different, or might not exist at all. This brings us back to the anthropic principle. We observe galaxies to exist in forms conducive to star formation and planet formation and life, because, if they did not, we would not be here to observe them. But it is worth appreciating how special this situation really is. The universe could have been more uniform, with no density fluctuations and therefore no structure. Or it could have been more clumpy, with fluctuations so large that only black holes formed. Or expansion could have been faster, preventing matter from clumping at all. Or dark matter might not exist, slowing structure formation so dramatically that galaxies never formed before the era of star formation ended. Any of these alternatives would have produced a universe without galaxies, without stars, without planets, without life. The fact that we exist to observe galaxies means we live in one of the rare configurations of initial conditions that generate structure. And even within that rare configuration, we exist at a special moment. Early enough that galaxies are still forming and evolving, providing dynamic environments for star formation. Late enough that several generations of stars have lived and died, producing the heavy elements needed for planets and life. Not so late that expansion has isolated every galaxy beyond observation. This is our cosmic context, a brief window in a vast universe where structure exists and can be observed. We live in an era when the universe still has structure, when galaxies are close enough to see one another, when stars are common enough that planets can orbit them and life can arise. In the deep past, the universe was too hot and dense for structures to form. In the deep future, it will be too cold and empty for anything to happen. We live in the narrow window between these extremes, a window that will close eventually, as expansion and entropy do their inexorable work. And yet, for all this talk of emptiness and isolation and eventual heat death, there is something extraordinary about the present. The fact that we exist at all is a miracle beyond any reasonable measure. The fact that matter clumped into galaxies, that stars formed, that at least one star produced planets, that at least one planet developed life, that life evolved intelligence, that intelligence built civilizations capable of studying the cosmos and understanding its past and future. All of this happened in an overwhelmingly empty universe that is becoming emptier every moment. Consider what had to happen for us to be here. The Big Bang had to occur with exactly the right initial conditions. Inflation had to happen, smoothing the universe and seeding quantum fluctuations of exactly the right amplitude. Dark matter had to exist in just the right abundance. Dark energy had to exist with exactly the right strength, not so strong that it prevented structure formation. The density of matter had to be precisely calibrated to allow galaxies to form without collapsing into black holes. Stars had to form and evolve, forging heavy elements through nuclear fusion. Those stars had to explode as supernovae, scattering heavy elements into space. Second-generation stars like the Sun had to form from gas enriched with those elements. Planets had to coalesce from debris around those stars. At least one planet had to occupy the habitable zone, the right distance from its star for liquid water. That planet needed a stable climate for billions of years while life evolved from chemistry. Life had to survive countless extinction events, asteroid impacts, climate upheavals, volcanic catastrophes. Evolution had to produce increasingly complex organisms over billions of years. Eventually, intelligence emerged. Consciousness capable of abstract thought and scientific inquiry. That intelligence had to develop language, writing, mathematics, science, technology. Civilizations had to arise that valued knowledge and invested resources in understanding the universe. Telescopes had to be built, observations recorded, theories developed and tested. Every step in this chain was improbable. Any one of them could have failed. If the density fluctuations had been slightly different, galaxies might not have formed. If dark matter did not exist, structure formation would have been too slow. If dark energy had been stronger, expansion would have prevented galaxies from collapsing. If the Sun had been slightly more massive, it would have burned too fast and died before complex life could evolve. If Earth had been slightly closer to the Sun, it would have been too hot for life. Slightly farther, too cold. If Jupiter did not exist, asteroid impacts on Earth might have been so frequent that complex life never had time to develop. If the Moon did not exist, Earth's axial tilt would vary chaotically, preventing stable climates. Every detail matters. Change any one thing, and we might not be here. This is sometimes called the fine-tuning problem. The universe appears finely calibrated for life, with many parameters set to exactly the values needed for complexity to emerge. Some physicists interpret this as evidence for design, for a creator who configured the parameters deliberately. Others invoke the multiverse, the idea that countless universes exist with different parameters, and we necessarily find ourselves in one where conditions permit life. Still others argue that we are still early in our understanding of physics and might yet discover deeper principles that explain why parameters have the values they do. All these perspectives have merit, and none is conclusively proven. But regardless of interpretation, the fact remains that we live in a universe hospitable to complexity and consciousness, and that universe is expanding. The expansion is not a bug, it is a feature. It is a necessary consequence of the conditions that allowed structure to form in the first place. Too dense and everything would have collapsed into black holes. Too empty and gravity could not have pulled matter together into galaxies. The universe had to expand at exactly this rate to produce galaxies and stars and us. And it is expanding faster now, because dark energy is accelerating the stretching, isolating structures from each other. Scientists cannot stop this process. They cannot reach out and grip the fabric of space and slow it down. No technology exists, and no technology is likely ever to exist, that can counteract a force operating across the entire cosmos, building up energy from the vacuum of space itself. Dark energy is not a thing you can neutralize. It is the property of the stage on which everything else plays out. But this process takes trillions of years. We exist in the era, when the universe is still full enough to observe and study, when galaxies are still visible in our telescopes, when the cosmic microwave background is still detectable, when we can still piece together the universe's history and predict its future. This era will not last forever. Eventually, the observable universe will shrink to contain only our local group. Then, eventually, only our own merged galaxy. After that, on timescales beyond comprehension, even our galaxy will dissolve as stars burn out and black holes evaporate. Heat death. Maximum entropy. Maximum emptiness. But that is trillions of years away. For now, we are here. We are conscious. We can observe and understand. We are a temporary pattern in matter and energy, emerging briefly before dissolving back into the void. But while we exist, we can observe, we can measure, we can understand. We can look at the expansion and calculate why it is happening. We can measure dark matter even though we cannot see it. We can detect dark energy even though we do not know what it is. We can trace the universe's history from the Big Bang to the present and project forward to the far future. This capacity to comprehend our own situation, to grasp the scale and structure and fate of the universe, is perhaps the most remarkable phenomenon in all of nature. Consciousness arising from matter, observing itself, understanding itself, recognizing its own impermanence, and doing so in a universe that is fundamentally, profoundly, terrifyingly determined to pull itself apart. We are islands of complexity in an ocean of void, temporary structures in an expanding universe, brief moments of order in a cosmos trending toward disorder. But we are real. We are here, and we understand why. That understanding does not change the physics. It does not stop the expansion or prevent the heat death, but it transforms the meaning of the expansion. A universe that expands and is never observed simply expands. A universe that expands and is observed and comprehended becomes something more. It becomes context, backdrop, the stage on which the drama of existence plays out. And the expansion itself becomes meaningful because it explains why we are rare, why we are special, why this moment matters. If the universe were static, if galaxies hung forever at the same distances without receding, our existence would not be remarkable. But they are not static. Galaxies are fleeing each other across millions of light years of stretching space. Most of the cosmos contains almost nothing, and that nothingness is growing. That makes the regions that do contain something, the thin filaments where galaxies cluster, the rare places where stars shine and planets orbit, profoundly significant. We exist in the exception, not the rule. In the rare pockets of density scattered through vast, widening emptiness. And we are conscious of that fact. We understand that we are rare, that our existence is improbable, that the expansion surrounding us is the norm, and we are the exception. This knowledge should change how we see ourselves and our place in the universe. We are not central, not privileged by location or cosmic importance. We are not the purpose of creation. The universe was not made for us. It simply happens to have conditions in certain rare places at certain rare times that allow complexity like us to exist. But that does not diminish our significance. It enhances it. Because we are the universe's way of knowing itself, the rare places where matter organizes into structures capable of observation and comprehension, where physics gives rise to chemistry, chemistry to biology, biology to consciousness, consciousness to science, where the universe looks back at itself and understands why it is expanding. The universe is expanding for reasons we now grasp. It began nearly uniform, with only tiny density variations. Those variations amplified over billions of years into the structures we see today. But expansion was always working against structure formation. And now, with dark energy driving acceleration, expansion is winning decisively. Structures are dissolving, voids are growing, the observable universe is shrinking. In the far future, everything will be isolated, disconnected, frozen, dark. Heat death. The final state of maximum entropy and maximum emptiness. But right now, in this brief moment between the Big Bang and heat death, the universe has structure. It has galaxies and stars and planets. It has life and consciousness and curiosity. It has us looking up at the sky, measuring the distances between galaxies, calculating the density of matter, inferring the presence of invisible dark matter and dark energy, tracing the cosmic web of filaments and voids, understanding how it all came to be and where it is all going. The universe is expanding. Yes, terrifyingly, profoundly, unstoppably expanding. Almost everywhere is becoming nothing. Almost all of space is being pulled away from itself. And the force responsible is mostly invisible, mysterious, understood only through its effects. The voids are vast. The distances are incomprehensible. The isolation is absolute and increasing. Dark energy is tearing space apart, accelerating expansion, pushing everything away from everything else. The cosmic web is dissolving. Structures are fading. The lights are going out one by one. Entropy increases. Order decreases. Complexity gives way to simplicity. The universe is running down, cooling off, spreading out, approaching its final equilibrium state. But in the small fraction of space that still contains visible matter, in the thin filaments where galaxies cluster, in the rare regions where stars form, in the vanishingly unlikely places where planets orbit at just the right distance for life to arise, something extraordinary happens. Matter organizes itself into increasingly complex forms. Atoms become molecules. Molecules become cells. Cells become organisms. Organisms become conscious. And consciousness looks back at the universe and understands it. That understanding does not change the expansion, does not reverse it, does not prevent the eventual heat death, but it gives the expansion meaning. Because an expanding universe that is observed and comprehended is fundamentally different from an expanding universe with nobody to notice. We are the universe noticing itself. Brief sparks of consciousness in an ocean of stretching darkness. Temporary patterns in an ever-widening void. But we are here now, and we understand why the universe is expanding. And that understanding, that ability to grasp the terrifying physics of cosmic expansion while existing as complex structures within it, that is not nothing. That might be everything that matters in this brief moment before the darkness returns, and the cosmos completes its long, silent fall into forever.